Welcome to module 18 of database management systems. We have been discussing about relational database design. This is the part 3 of that. In the last module, we discussed about the notion of functional dependency and decomposition based on that at an elementary level and a certain bit of its theory. In this current module, we will learn different algorithms that use the functional dependencies and can make conclusions about the design or make changes to the design. We will also try to understand the characterization for lossless join decomposition and the notion of dependency preservation. Therefore, this module will have these three topics: algorithms for functional dependencies, lossless join decomposition and dependency preservation. So, first we start with the algorithms, and I quickly reproduce where we had ended in the last module in terms of computing the closure of a set of attributes. So, if we have a relation having these attributes and a set of functional dependencies, then for a given subset of attributes, in this case A g, we can iteratively compute the closure set when no further changes can be done. And with using that, we can make different conclusions. For example, if our question is whether A g can be a candidate key, we would first like to check whether it is a super key, that is whether its closure has all the attributes of R, and we would like to check if we take a subset of A g, if we take just as attribute A or attribute G, whether the closure of that will actually work as a key or not. So, this algorithm of attribute closure turns out to be a very powerful one, where as we have just seen, it can be used for checking super keys, candidate keys, primary, non-primary attributes and so on. It can be used for checking functional dependencies. For example, let us suppose that if we have to check that whether a particular functional dependency alpha determines beta holds, then or rather in other words, whether alpha determines beta is in the closure of the set of functional dependencies f, then all that we need to do is to compute alpha plus, that is a closure of the set of attributes on the left hand side of the dependency, and check if beta is a subset of that. If beta is a subset of that, then I know that alpha determines beta actually holds. So, in this manner, it can also be used to compute the closure of the whole set of functional dependencies f. So, if we at least at a rudimentary level, we can think of that if we take any subset of the set of attributes and find the closure, and then all attributes that belong to that closure set are actually functionally dependent, and therefore, those functional dependencies will exist. Now, we move forward from there and talk about what is known as a canonical cover. A set of functional dependencies may have a number of redundant dependencies also. So, we need to understand that, because there are a lot of dependencies which can be inferred from a certain set of dependencies. For example, if you look into this set, you will easily understand that in this whole set, if I actually have just this, we will be able to, by transitivity, we will be able to conclude about A determining C. So, in that way A determining C is a redundant dependency. So, here I am just showing you some examples. So, for example, say I have a set of functional dependencies as this set, and I want to know whether I can replace it by a simpler set here, where this particular attribute on the right hand side of this dependency may be extraneous. So, if I have to do that, then what we need to perform is we need to show that given the set of functional dependencies, the original set, whether this can imply this set, that is, from this set of functional dependencies, whether I can logically conclude the simplified set. So, using the rules we will need to do that. I have worked that out here under the forward scheme, And we would also need to establish that if I have the simplified set, then can I go to the original set that was given. So, if the simplified set also logically implies the original set, then we can say that these are in a way equivalent, and therefore, I would like to use the simpler set. So, there is another example following here, where I have another set given, where if you look into this, I would like to check whether I can get rid of this C on the left hand side, and as it stands, we can actually do that. And here in this whole process, I have shown it in terms of using the Armstrong's axioms, how you can prove this, but what we can do to systematize this whole process, we can again make use of the notion of closure of attributes and compute whether these two sets are equivalent, whether simplification can be done. So, we will say a cover is canonical if it is in a sense minimal and still equivalent to the original set of dependencies, and we will formally introduce what is minimal. Before that, let us just look at the same examples again. So, we are trying to show the forward direction in the first case and the reverse direction in the first case, but the only difference that I wanted to highlight is in terms of showing that you do not need to really explore on the Armstrong's axioms, but what you can do is you can simply take the left hand side attribute and compute a closure and see whether the right hand side is included. That is basically testing for whether the given functional dependency is actually implied. Similar things can be done to simplify the left hand side also. So, this is the other example that I showed, and I am just showing you that how you conclude this based on the closure of attributes algorithm. So, now I can formally define these possible removals. So, if I can remove an attribute, as I have shown, I can remove it from the right hand side or I can remove it from the left hand side. So, if an attribute can be removed, then it is called extraneous. So, if I have a functional dependency, let us say alpha functionally determines beta, and I have an attribute A which belongs to alpha, then we can check whether it is possible to remove A from alpha. So, to test that, what we do is we form a new set by removing the original functional dependency and adding the new functional dependency where the left hand side does not have that A. And if F logically implies this, then certainly we can conclude that A on the left hand side of the functional dependency was extraneous. Similar thing can be done for checking if there is an extraneous attribute on the right hand side of a dependency, and in this case naturally what we will need to do is we will need to work out the simpler set and then check whether F is implied by that, because as you can understand that if you are making the left hand, if you are removing an attribute from the left hand side, then you are making your precondition softer. So, you need to see whether that is implied by the original set, and on the other hand, if you are removing something on the right hand side, then you are making your consequence simpler. So, you need to understand whether that set implies the original set. So, if you look into that, and obviously, the other directions of this implication is not necessary to be proven, because that will automatically follow, because in the first case when I am removing an attribute, extraneous attribute from the left hand side of an of a functional dependency, naturally the set that I get, that will always imply the original set, because it is always possible to add additional attributes on the left hand side and so on. So, here are some examples worked out. So, here where I show that given a set A C and A B determining C, B is actually extraneous, because as you can see, if I remove B, then I get A determining C, which is originally already there in the set. You can establish that by computing the closure of the attribute set. Another example where you are trying to see an extraneous attribute on the right hand side. So, in this example, C on the right hand side of the set, A B determining C D is extraneous, because it can be inferred even after because A B determining C can be inferred even after deleting this C from the right hand side. So, these are using this notion, we can formalize a test for whether an attribute is extraneous. So, this is the formal steps of the step are given here, but I am sure you have already understood through the example. So, given this a canonical cover of a set of functional dependencies F, it is denoted by F C, will mean that it is a set which is equivalent to F, which means F will logically imply all dependencies in F C and F C will logically imply all dependencies in F. No functional dependency in F C will contain any extraneous attribute. So, all of them will be required attributes, and each left hand side of the functional dependency in F C must be unique. So, it is a minimal set of functional dependencies. Please note on these two core points, a cover is canonical if it is a minimal set, and it is an irreducible set. So, neither you can remove any dependency nor you can remove any extraneous attribute from this dependency set. So, here is the algorithm. So, I am not going through the steps of the algorithm, you can go through that and convince yourself that it indeed computes the canonical cover and practice more on that. So, here I have shown an example where we want to compute the canonical cover here. So, first since all left hand sides have to be unique. So, first we combine these two in terms of A determining B C. So, it becomes a simpler set. So, A determining B is removed, then I would check for A being extraneous in A B determining C, and we find that it indeed is extraneous. So, because B determining C is already there, you can do the formal test in terms of the closure. So, the set gets even simpler. I will check if C is extraneous in A determining B C. I find that it indeed is, and again you can use transitivity to get here, or can use the attribute closure, and finally, I get that the set of the original set F is covered by a canonical set, where just you have A determining B and B determining C. So, this set is logically implied by the original set, and this set can logically imply the original set, and we will often use the canonical cover for simplicity and for ease of application. Naturally, this is strongly using the underlying concept of equivalence of two sets of functional dependencies F and G. They are equivalent if their closures are equal, or in other words, if F covers G or and G covers F, that is F logically implies G and G logically implies F. So, this table shows you different conditions where you can conclude whether F and G are equivalent sets of functional dependencies. So, they will have to, both covers have to be true for the sets to be equivalent. What I have done is we have put a number of practice problems for various kind of things that you can do with functional dependencies. The first set of problems find in first set of problems you have to find if a given functional dependency is implied from a set of functional dependencies. So, there are three problems where three sets of functional dependencies are given, and you are given to check one or more functional dependencies if it is implied from that set. So, use the attribute closure and the algorithm that we have discussed to practice these problems and become master of that. You can also check if can find candidate key using the functional dependency. So, sets are given, your task would be to find the candidate keys. You can also use the algorithms to find super keys for a given set of functional dependencies. So, do practice these problems. You can find prime and non-prime attributes using functional dependencies. Prime attributes are attributes that belong to any candidate key, not necessarily the same candidate key. All attributes that belong to some candidate key, you take a set together and you call them as a prime attribute, and non-prime attributes are those that do not belong to any candidate key at all. So, here your task is to find the prime and non-prime attributes using the sets of functional dependencies given. You can check for equivalence for a pair of sets of functional dependencies. There are a couple of problems given on that. So, please try them out, and for here for the different sets you have to compute the minimal cover or the irreducible set or canonical cover of the set of functional dependencies. So, please practice on these problems, so that you become comfortable with using these algorithms for dealing easily with the functional dependencies, sets of functional dependencies, individual functional dependencies, and so on. So, after this week is closed and your assignments are also done, then we will publish the solutions for these practice problems as well. Next, let me take up a little characterization of the concept that we had introduced earlier in terms of the lossless join decomposition. So, in the lossless join decomposition, the problem is say that you have a relational scheme R, and you are trying to divide that into two relational schemes R 1 and R 2. So, both R 1 and R 2 are having a set of attributes, and R naturally has the set of attributes which is a union of the attributes of R 1 and R 2. Then is it possible that if I take a relation, project it on the attributes of R 1 and on the attributes of R 2, the two relations that we get, if I take a natural join of that, do I get back R? If I do, then I say that I have a lossless join. If I do not, then I have lost some information due to this projection and recomputation of the original relation based using the natural join. The requirement, this requirement of lossless join decomposition is determined if at least one of the following dependencies exist in the closure set of F. What are these? It is saying that if I do R 1 intersection R 2, that is the attributes which are common. You will recall that when you do natural join, it is this set of attributes which take part, because these set of attributes will help you compute the join between projection on R 1 and the projection on R 2. So, if this intersection set of attributes uniquely determines R 1 or it uniquely determines R 2, that is, if the intersection set of attributes is a super key either in R 1 or in R 2 or both, then we say that the join will be a lossless join. Note that this is a sufficient condition, that which means that there could be some instances where this property is not satisfied, yet the join is lossless, but we need guarantees for our design. So, we make use of the fact that if one of these conditions are satisfied, then it is a sufficient condition to say that the join will necessarily be lossless. So, here I give you a quick example to show the idea. So, we have a supplier relationship here which has 5 attributes. Here is an instance of that, and we know that these are the dependencies that hold. The supplier number determines the supplier name and the supplier city, and supplier number and product number together determines the quantity, and we decompose them in this manner. We put a supplier relationship where we have the number, name, city and quantity of supplier, and then we have a parts relation where we just have a product name and the quantity. And then so this is the projected supplier relation instance, this is the projected parts relation instance, and then we take a natural join to reconstruct. So, we are taking a natural join to reconstruct and we get this relationship. Now, our desire was that we must get back the original relation, but if you compare, you will find that this is not the case. Here we have one tuple here and we have another tuple here. I have specifically highlighted them in red, which were not there in the original relation. They have come in because when I did the join, naturally the join had to be performed on this common attribute quantity, and based on that value. So, NIC 5 NIC NY, the 5 NIC NY, then we have 10 5 NIC NY 10 this entry, and we have 2 entries of 10 and 10 here. So, the combination of this with this, where the product number is 20, is actually not present in the original instance of the relation, and that is what shows up here. A similar one exists here. So, we get extra tuples, and mind you, though we are actually getting extra tuple, we say that this join is lossy, because if you get extra tuple, then you are losing information, you are losing correctness. So, being lossy is actually losing correctness. So, even though we have more tuples, we say that this is a lossy join, and you can now go back and analyze that the common attribute QTY is not a super key either in this or in this. So, R1 intersection R2 implying R1 or implying R2 does not hold. So, it does not, and in addition it also does not preserve this functional dependency, because these are not no more determined. Now, let us see, is it so we saw a case where the join, the decomposition that we did and then the subsequent join that we performed did not prove to be a lossless join, we lost information. So, let us take a look as to, can we actually do a decomposition which will be lossless, where we will not lose information. So, I take the same example, the supplier, but the decomposition, the same set of dependencies also, but the decomposition is different. Now, we have name, number, name and city in one supplier relation, and supplier name, number, product number and quantity in the other parts relation, and then we again go back and perform the join. Now, we find that from the original relation, this was the original relation, this is the projected supplier relation, this is the projected parts relation, and this is the natural join of these two relations. So, this is the natural join of these two relations, and we find that they exactly match with the original relation. So, we have not lost any information, we get it back. So, we say that the join is lossless, and the reason we could guarantee that is because if you look into the set of functional dependencies, you will find that S number, the supplier number is a key in the supplier relationship, because it functionally determines S name as well as S city. So, R1 intersection R2 functionally determining R1 is true here, and therefore, it actually gives you a lossless join. It also preserves all the dependencies, because if you look into these dependencies, you can check for this dependency in this relation, you can check for this dependency also in this relation, and you can check for this dependency in also in the parts relation, which is something which we were not able to do in the last decomposition that we have. So, naturally, this is a type of decomposition that we will prefer. So, here we have I have given some more examples which you can practice, and I show that given a very simple schema having 3 attributes and 2 dependencies, one decomposition into A B and B C is lossless join decomposition, whereas the other one A B and A C is a lossy decomposition. I have given a number of practice problems on lossless join, so that you can practice and become master of these kind of algorithms. Finally, let me quickly go over the dependency preservation concept. The dependency preservation is if you have a relation which you have decomposed into n different relations. So, if you decompose a relation into a number of relations, then naturally all functional dependencies you cannot check on all the relations, because a dependency may involve attributes, all of which may not be present in a particular decomposed relation that you have. It may be distributed amongst different. So, when you do this decomposition, you get, for every relation you get a new set of a subset of functional dependencies. So, R I, the decomposed relation R I, the ith relation, will have a set of dependencies F I, which is a subset of the original set F, and involves only the attributes which are exist in R I. So, the decomposition will be said to be dependency preserving if I can take the union of all these functional dependencies, what is projected on R 1, on R 2 and R n, F 1, F 2, F n, if we can take union of, and if we take F, they must be equivalent sets. So, which we know the we know the requirement. So, equivalence mean that they will, their covers will have to be equal. If it is not, then there will be at least one dependency which you will not be able to check in any one of the projected relations, and to be able to check that, you will have to compute the natural join, and that is, as we know, is a very expensive process, and we would not be able to do that on a regular basis. So, here I have written down the algorithm to test if a decomposition actually preserve the dependency or not. So, I will not go through the steps, I will leave that for you to understand, but what I will do, I will just show you a simple set of worked out example and reasoned on that. So, I show you two different methods of doing this. So, here we have a set of attributes given, the dependencies that work in that, and a particular decomposition. So, given the set of attributes and the decomposition, if we project now, if we project the set of functional dependencies, then these are the sets that we get. So, on R 1 we have 2 dependencies, on R 2 we have 1 dependency, and on R 3 we have 1 dependency again. So, if we now think about the union of these and the closure for that, then we can see that these 4 dependencies which occur here, and therefore, I have struck them off in this set. These 4 dependencies can be checked directly on the projected relations. So, that leaves us with 3 dependencies in the original set, which cannot be checked on any one of R 1, R 2 or R 3. For example, if you consider B C determining E, then B exists on R 1 and C also exists on R 1, but E is not there. So, you cannot check that dependency on R 1. You cannot check that on R 2 because C and E do not exist, and you cannot check them on R 3, check it on R 3 because none of them actually exist. So, what we will need for the dependency preservation to hold is the dependencies which are already existing, the 4 dependencies that are struck off, if they collectively can logically imply these dependencies so that they can be checked, then we will be able to say that this is dependency preserving. So, what you do is something very simple. You want to say, you want to check whether this is preserved. So, you start with the left hand side and compute the closure. The only difference, you compute the closure first with the set of functional dependencies projected on R 1, that is F 1. The set closure set that you get, you take that and compute its closure with respect to the second set of functional dependencies F 2. The closure that you get, you take that and you compute the closure with respect to the third set of functional dependencies, which is on R 3, and that is your final closure set. So, this closure set includes the right hand side attribute E. So, we can conclude that B C indeed functionally will determine E, and that relationship will be preserved, because we have, starting from B C, we have seen that in every projected relation what all implied functional dependencies that can be checked, which is what the meaning of the closure set of attributes are. And since that set eventually has E, we will know that this will be preserved. This set also has F, so the other one will also be preserved. So, this is preserved, this is preserved. To check whether this dependency is preserved, we need to again repeat the process and find whether E f belongs to the final closure set, which it does, and therefore, we conclude that this decomposition is dependency preserving. With the same example, I will just show you a little different way of doing the same exercise. I have not written down the algorithm for this in longhand, but the example should be quite illustrative. So, here what you do when you project, you check if some dependency has multiple attributes on the left hand, on the right hand side, then you write them in a separately decomposed manner. So, A implies determines B, C, D is written in terms of 3 dependencies: A implies B, B implies C, and C implies D. So, you make sure that all dependencies are written in a form where the right hand side has a single attribute. Then you compute what is known as the reverse functional dependencies, that is, you take the right hand side and compute whether the right hand side can imply the left hand side. So, I will just show you one. So, in case the right hand side here is B. So, you have a B on the right hand side. So, you compute the closure with respect to F, the original set, not the projected set of, and you get B f. So, you know that this reverse functional dependency, which is B functionally determines A, which is the reverse dependency, cannot be inferred. And you do this for each of the right hand side single attribute and check if the reverse dependencies can be inferred or not. The interesting case occurs here, where if you try to do the closure of A, you actually find that A determines B c, which is a reverse of this functional dependency, can be inferred, but you do not consider that as a violation, because it is, you already have A determining B and A determining C. So, that logically implies that A determines B c. So, it is not a new violation that is getting imposed. So, with this, your test for reverse functional dependencies is passed, and then you finally check for whether the 3 dependencies which are not part of the projected set of dependencies, you take the closure of the left hand side with respect to, in this case, again the original set of functional dependencies, not the projected one, and check if the right hand side belongs there. If they do, then combined with these 2 strategies, you say that the set of functional dependencies are preserved under this decomposition. So, this is the process to follow. You can follow any one of the 2 approaches to solve, and I have given some practice problems on dependency preservation, which you should practice on. To summarize, we have studied the algorithms for properties of functional dependencies, and we have understood the characterization and determination algorithm for lossless joint decomposition and for dependency preservation in a decomposition. In the coming module, we will make use of these and discuss about how to improve designs of relational schemas through the use of different normal forms.